of us. I know you all did the take-home quiz, all 9 of you that forgot to do it last time. So here we go. Number 1 says, given the following point configuration, find the magnitude of electric force between 2 charges. I'm going to go a little bit quicker for some of these. Number 1, because this is straight plug and chug. It's force equals KQ1 Q2 over R squared. By the way, remember, we now have 2 equations for force in this unit. We have force equals between 2 point charges, but then we had our generic equation, which was force equals charge times electric field, which is this equation in disguise. You get 2.4 times 10 to negative 2 newtons. You do not put negatives and positives in for forces and fields. You forget the signs. B. I like B, I like B, I like B. Find the electric field between 2 charges. So we said what you're going to use is the principle of superposition. You're going to temporarily pretend this charge doesn't exist. Find the electric field from this charge. No sign. It's KQ1 over R squared. It's 9 times 10 to the 9th times 5 times 10 to negative 6 over R squared. It's 20,000 newtons per coulomb. Direction. Which way would a positive charge right there want to move because of that guy? It would be attracted to the left. Find the electric field of the second charge, KQ2 over R2 squared. You get 37,370 newtons per coulomb. Direction. Which way would a positive charge right here want to move because of this guy? It would be repelled to the left. So they're both to the left. I get left plus left. So you know what, John? I'll just add them up. I don't go winner minus loser. They're both winners. I got 5.7 times 10 to the 4th newtons per coulomb. And then direction, half mark, left. Or you could say west, but since I didn't throw a compass on there, I used left and right. C says find the electric potential at location A. Find the electric what? Did they say energy? Don't be going KQ1, Q2 over R, energy. It's not. Potential is an archaic word for voltage. So to find the voltage at location A, what I'm really going to do is find the voltage from the first charge, find the voltage from the second charge, and add them together. How am I going to do that? Well, voltage is KQ1 over R. Voltage is a scalar. Terry, put the signs in for a scalars. So I actually end up with a negative voltage from the left-hand charge, a positive voltage from the right-hand charge, and when I add them together, I get 1.76 times 10 to the 3rd volts. You get 1,764, but to 2 or 3 sig figs, 1.76 times 10 to the 3rd volts. That means at location A, every single coulomb of charge that you put there has 1,764 joules of energy. That's what voltage is saying. Next page. Number 2 says, suppose we have a fixed charge of magnitude. So a fixed charge, I had to dulp. I drew my little fixed charge right there. Fixed means held in place, can't move. How much work, oh, and I said the charge is negative 8 microcoulombs. How much work would it take to move an electron from an extremely large distance away, over here, to a final location 0.15 meters removed from charge Q1? What are they asking me to find? How much work? I can't use force times distance. There is no area under a graph. It's going to be change in potential plus change in kinetic, except I didn't even bother writing change in kinetic. I said, I think we're talking about starting and ending at rest. Potential energy is KQ1, Q2 over R final minus R initial. Final minus initial. Potential energy, Ben, scalar. Put the signs in. Now here's the nice thing. When I put a negative in and a negative in, what's a negative times a negative, Ben? I do get a positive amount of work. Oh, why did I cross out R initial? Out at infinity, how much potential energy do I have? Cool. Okay. Number 3. What are they asking me to find in number 3? Is there a change in height? Is there a change in speed? This is a job for conservation of energy. Now, you may say, it's not a change in height, but use your imagination instead of moving up and down, left, right, but there is a change. Yeah, the distance, the radius is changing. So I said, you know what? It's going to be kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Got me 1 mark. Oh, and I said we're starting at rest, so I crossed out kinetic energy initial. I got the kinetic energy final by itself. And then I said this is a half mv squared equals, okay, this is not mgh. We're talking about electric potential energy, which is k q1, q2 over. This was kind of strange, Ty. I had initial minus final. I had negative change in if you really wanted to be fussy. Although that kind of makes sense because whatever potential energy I lose, kinetic gains. The negative does work out to the positive of kinetic. You know what? Okay, I'll go with that. I carefully crunched the numbers. I said put the signs in, although everything here was positive, so it didn't make a difference. I found that I ran out of room, so I wrote same thing on the top over here, or ditto marks or whatever. I was just running out of room. I found this wasn't worth trying to get the V by itself yet. I crunched this and I carried it to 4. I think, in fact, I carried it to 5 or 6 sig figs on my calculator. So I carried, in fact, I kept this number right here in my calculator. How would I get V by itself? Times by 2, divide by m. Which mass? It's a proton. By the way, on your test, I'm going to be shooting protons and electrons around. Please clue in, Terry. You have the charge for both of them, which is the same on your sheet. You'll need to know whether it's negative or positive if you need to. And you have the masses on your formula sheet. Don't freeze. Oh, why don't you give me the mass? The masses don't cancel, Mr. Dude. Yeah, I didn't need the, it's a proton. Anyways, 2.6 times 10 to the 6 meters per second. Speed of light's 3 times 10 to the 8th. We're going fast, but 1,000 times slower than the speed of light. 100 times slower, sorry, than the speed of light. So pretty fast, but not crazy fast. So last day we looked at parallel plate force problems. We described a little bit of how lightning worked. We said that if you have a large enough electric field, you can ionize the atmosphere with some nice applications. In the homework that I gave you, today's lesson is going to be on what we call parallel plate energy problems. So I normally, and I will start out by saying, hey, any questions from the homework? However, what I'm going to say is this. If you have a question about number 6 or number 8 or number 9, specifically about finding the final speed, I'm going to show you a better way to get there today using energies. You can get there by calculating the force, dividing by the mass, getting your acceleration. VI is 0. What's VF? I know the distance. That's all doable. But there's a better way. Having said that, then, were there any questions from the homework? Yeah. Number 4. Okay. So what we've been saying is this, my friend. Number 4. Oh, come here. Jake, is that equation on your formula sheet? Not directly. It's in your formula sheet as the definition of electric field as force per charge, but that must mean that I can get the force by itself. Yes. So far, so good? Specifically, that little q is the charge that's sitting at that location, which in number 4 is 2 microcoulombs. Times, and remember, Jake, that's electric field, not energy. We're running out of letters. Did they tell me the electric field in the question? Well, we also know that the electric field between plates is the change in voltage divided by the distance. Did you see it now? Yes. So really, what I'm going to do is this. Did they give you the voltage? Yep. Did they give you the distance between the plates? Yep. And by the way, on your reviews, and I know on the provincial, and I think on your test, if they give you a picture, often they'll give you 2 distances. They'll give you the distance between the plates, but just to confuse you, they'll give you the length of the plates as well, because they want to, give you extra information, Taylor, and try and confuse you, because it's also a distance. It's got a centimeters or a meters next to it. It's the distance of separation between the plates. Is that okay? Yeah. Jake? Any others? So 6, 8, and 9, yeah. Number 10, yeah, that I can talk about. Okay. So it says, find the charge on the particle below. Assume the particle is at equilibrium. What that means is the net force on it is equal to 0. What are the forces acting on it? Get the obvious one. Yeah, this is a big enough charge now. It's not an electron or a proton. It's going to make a difference. We have gravity down and electric force up. In fact, we're going to get this. Now, don't write this next bit down. I can't go K, Q1, Q2 over R squared, because how many charges are there in my picture? This one needs 2. Oh, you know what? I'm going to use the second definition of force that I just did with Jake. Q times the electric field equals mg. Oh, Jake said, hey, wait a minute, Mr. Dewick. Oh. And then get the m by itself. Is that right? Oh, did they want the mass? No, sorry, they want the charge. Get the q by itself. Read the question, Mr. Dewick. And they gave me the mass in the question. It's going to be... Right? Yep. Is that okay? And that was the famous Michelson experiment. That's how he found... Oh, sorry. Millikan experiment. That was how he found... I think it was Millikan. Is that what I told you guys? We watched the little video. Where was it, Mr. Dewick? Yeah, Millikan. That's how he found the charge on an electron. Okay. So, if you got 6 and 8 and 9, the speeds, fine, you can hand it in, but I'm going to show you a better way today. So if you guys have the homework done, you can hand it in today, or you can hand it in. Here we go. Parallel plate energy problems, situations. So remember, for parallel plates, the voltage is given by the battery or whatever you hook it up to, or we'll just label it on the plates. And remember, it varies directly with the distance between the plates. That's handy. Now, here's what we said. For a test charge placed at a point whose voltage is known, we can find the potential energy using say what? Well, remember, we defined voltage as how much potential energy every unit of charge had. So if I get potential energy by itself, that leaves me with the equation in the little box there. By the way, this is the day when you're going to be doing an equation that has V velocity lowercase and V voltage uppercase. So this is where you either want to make sure you can distinguish between a lowercase v and an uppercase V, or like my prof told me, this is where I start doing the wings on the capital V big time. Example 1. Says find the work done by an external agent that moves a 2.5 microcoulomb charge from the from the negative plate to the positive plate. Assume the charge begins and ends at rest. First of all, which way does that charge want to move, up or down? Down. It wants to be towards the negative and away from the positive. So will you have to lift it up? They called it an external agent. I always just imagine little invisible angels or whatever. Whoever's lifting it up, will they have to do work? Yeah, this is just like you guys lifting up a heavy weight away from the earth. Okay? Did I say work? Work is force times... No, I don't see a force here. Work is the area underneath a force... I don't see a graph here. Oh, I think work is... Right? Oh, and why can't I do that? Yep. And Josh, what's changed in anything? Yeah. This is a better way. We can say instead that potential energy is the charge that you're moving. No, leave it exact. I did this on purpose, by the way. I want you to realize that we can use this approach, but there's a better approach. Come on, you think I did that? Come on. Leave it like that and say, actually, for this specific situation, Megan, between parallel plates, I think a better way would be to say, look, If the potential energy at any one point is given by the charge times the voltage at that point, how about the total energy that you climb through? Wouldn't it be the charge times the total voltage that it climbs through? Which is way less work than going final minus initial. In fact, this is the equivalent of MGH, potential energy lifting something, except instead of mg and h, I'm saying, you know what? Instead of mq, the charge that you're moving, how big it is, and instead of gh, remember I did say voltage was sort of like height, kind of. How big is the charge that we're moving? 2.5 times 10 to the negative 6. How many volts are we traveling through grand total? 120. Hey, what if I asked you how much work to lift to move it halfway through this voltage? It would be 2.5 times 10 to the negative 6 times what? Yeah, 6. If I wanted to get exactly right there, I just multiply by 60, because remember we did say the voltage increases linearly in a nice straight line. What if I wanted to move 1/10 of the way up? Oh, 12 volts. Right. It's a much quicker approach. Final minus initial would still get us there, Megan. This is way cleaner. And again, this is also a side benefit of that whole rant about between parallel plates, I have a nice constant electric field. That means my force is constant. It means I can take some shortcuts. What's the answer? How much work? Not going to be very much. Sorry?
3 times 10 to the 4.
3, how about 3.0? We'll go to 2 sig figs. Times 10 to the negative, I'm sorry?
4.
4 units? Joules. Don't write this down, just watch. What if instead I set this up with the 120 there and the 0 there? Which way would this charge want to travel now? Which way would this charge want to, yeah, in fact, it would want to, and I'll use the word, fall up. This is like dropping something. I wouldn't ask you how much work because it wants to go up, but I could say how fast is it traveling when it hits the ground. It's not the ground, but you understand the analogy. How fast is it traveling when it hits the far wall? That would be, is there a change in height? Is there a change in speed? That might be a job for conservation of energy. That would be how I would handle number 6 and number 8 and number 9 from last day when they said find the final speed. You could find all the forces and acceleration. In fact, I'm pretty sure the next question we're going to look at, I think, if I did my job right, yeah, example 2. What's number 2 asking me to find? Final speed. This is actually an electron gun. What we have is a heavily negatively charged plate here, repelling it. Compared to the negative, this is positive. I know it's got a charge of 0, but it's net positive compared to this. But what we do is we have a small slit or a small hole so that as long as this group of electrons travels straight, they'll come shooting out. Now, some electrons will run into there and run into there. I don't care about that. What I do have, if I do a very, very fine slit in that parallel plate, I've got an electron gun. I've got a beam of electrons coming out. How fast? Is there a change in height? Is there a change in speed? This is a job for conservation of energy. Also, they're not saying how much work. This is how I would do number 6, the last part, find the speed. And number 8, the last part, find the speed. And number 9, the last part, find the speed. Oh, I would say to myself, and once it gets to the far wall, how much potential energy does it have left? That's like it's hit the ground, except we've drilled a hole in the ground so it can keep falling. But here's where our gravity analogy breaks down. It's going to keep falling without speeding up because somehow gravity stopped acting once it hit that hole in the ground. But this is just like dropping an object. We would say, this hasn't changed all year long. Now we have a whole bunch of different equations for potential energy. This is electric potential energy between parallel plates. This is the equation that has the two V's. This is the situation that has the two V's. That is potential energy, isn't it? Q times, it's technically Q times the change in voltage, but look at my picture. Can you tell me what the change in voltage is going to be, what voltage we're traveling through? 125, so I get sloppy and drop the delta. Just like for time, we get sloppy and drop the delta. What do they want us to find? V final? Let's get the V by itself. How? Times by 2, divide by m, and then square root. I think we end up with this. 2q v divided by m square root. 2q. Uh-oh. It's an electron. Mr. Dewick. Yes, Josh. Or was it someone asked me, was it in this class? I think it was in this class. Maybe it was in my block B. Shouldn't I be sticking negatives in because this is a scalar? Now here's the problem. If I put a negative into a square root, what's going to happen when I try square rooting? Okay. You know, here's the answer, by the way. Technically, yes, you can put the negative electron in, and then you can argue that the change in that it's traveling, because we define electric field as which way would a positive want to go if it could, a positive charge would be going through a change of positive 125 volts, whereas a negative charge could be going through a change of negative 100. You know what? You can just remember for this specific situation, because you're taking a square root, don't be putting negatives in. Can is that an easier way to do it? But for what it's worth, it is consistent with everything else we said. I'm going to put 1.6 times 10 to the negative 19. V, 125. So you could argue it's negative 125 is where we're starting, but anyways. Mass, it's an electron. I know it's 911. It's 9.11. Negative 31? By the way, the speed of light is 3 times 10 to the 8th. Don't be getting an answer bigger than that. It probably means you forgot to square root. What do you get? You should get something in the 10 to the 6th, 10 to the 7th range, I think. Yeah, it's going to be going fast. 6.63? Not negative, Mr. Dewick. Positive 6? Well, Mr. Dewick, you said that the speed of light is the fastest we can go. Couldn't we put this through a bigger voltage? And if I had like a bigger number there, like maybe added a 0, wouldn't that make that a 10 to the 7th? And if I added another 0, wouldn't that make that 10 to the 8th? Well, first of all, this is what they're doing at the Large Hadron Collider, and you can see why they need big voltages, or why they have a huge power source. It's more complicated than that, but this is how you can get an electron or a proton or a charge up to speed. But this is then where relativity kicks in. As it turns out, the faster you go, something amazing happens. As your speed approaches the speed of light, something else gets bigger that's also in this equation. Turns out the mass starts to increase. And it increases at a faster rate than you can increase the speed. I think they get the Large Hadron Collider, it's like 99.9999% of the speed of light. It's not quite there. And that takes, I mean, basically, they're using the power of a couple of nuclear reactors to do that. So it goes very quickly off the scale. But sorry, speed of light is still a cosmic speed limit. Now, mathematically, we have postulated that there are particles that travel faster than light. We call them tachyons. They're made up. Tachyons from the same root word as tachometer, the word in Greek for fast, for really fast. We can't prove if they exist or not. If they did exist, they would have some very strange properties. Because they're going faster than light, they would actually be traveling backwards in time, which means if you sent a message to somebody with tachyons, they would receive it before you sent it. That's perfectly consistent with Einsteinian physics. And that would make for some great pranks. Anyway, okay. It would. I mean, I know what I would. Yeah, okay. Right, Mabad would get something. Duck. What? Whack! Oh, jeez. Ah, yeah. Okay. So, as we see from the above calculation, when a particle is accelerated from rest by voltage, we have a simple energy equation. All of the potential turns into kinetic, just like when you drop something and it hits the ground. All of the gravitational potential turns into kinetic. We must take care in this equation not to confuse voltage V with speed V, and I made a little note here. This is the one scalar where we don't put the signs in, and you'll notice it because if you do put the sign in, Alicia, your calculator will give you an error when you try square rooting, and you're clever enough then to go, oh, Duick said don't put a negative inside a square root. We get this. In this case, we solved for speed, but you can use this to solve for whatever. Let's invent a television. Now, this next couple of 20 minutes used to be great. It was great back when we had televisions that weren't flat, thin screen plasma screens, because flat, thin plasma screen works on a totally different principle. But remember the old colored IMAX? Any TV screen that when you look at it from the side, you have a curved screen, but then you have that huge box going back like that, okay? That's called a cathode ray tube. That was the television technology for about 80 years. And there are still some monitors that use that technology. So sadly, this isn't quite as up-to-date as it used to be. And I will show you later on today, or perhaps on Friday, how a flat screen panel works. But for now, example 3, an electron already moving enters a set of accelerating plates. Find its speed when it leaves the plates. Terry, is there a change in height? Is there a change in speed? Is it saying speed? That's all indications that a scalar conservation of energy approach is your best bet. This time, I can't... Whoop! I didn't want to do that, Mr. Duke. No, I didn't want to do that either. This time, I can do that. Can I cross out my initial kinetic energy, though? No, this time it's already moving. Okay. So it's going to be a half mv initial squared plus q change in voltage equals a half mv final squared. Do the masses cancel? No, because there's not a mass inside that potential. And you know what? I mean, I could try and get the V, but, well, maybe. Let's go times by 2, times by 2, times by 2. We did this trick before because that got rid of the halves. Yeah, it leaves a 2 in front of your middle term, but I'd rather have a 2 in front than a bunch of 1/2s kicking around anyways. What else is sitting next to the V? With the V final. Sorry, too many V's in there. What else is sitting next to the final speed? Mass. How would I move that over? And then how do I get rid of a squared? You know what? This is we can rewrite this. It's complicated, but I think V final is going to be big square root of mv initial squared plus 2q big V all divided by the mass. I think. Is that right? You know what? This is I probably should have just started crunching numbers and then got the speed by itself. But we've come this far. Dorothy, let's see if we can take the challenge. Final speed is going to be big, huge square root. Mass. It's an electron. Which is also going to be down here, right? V initial squared, 5 times 10 to the 5th squared, plus Q. It's an electron. Oh, sorry, plus 2 times Q, 1.6 times 10 to the negative 19. How many volts? Oh, careful. How many volts are we traveling through? Don't say 600. What? 500, because our initial voltage wasn't 0. Okay. Oh, you know why we did that? Because that way this positive would yoink this electron in and get it up to some speed before it hit this slit and kept going through. There you go. Okay, I can do this. Divided by 9.11 times 10 to the negative 31. What? Oh, square root, Mr. Duke. Do you get 1326? Holy smokes! Do you get something that works out evenly? Oh yeah, I guess because the. Sorry. 1.33 times 10 to the 1, 2, 3, 4, 5, 6, 7. Getting closer to the speed of light, but not quite. About 10 times slower than light. Well, about 20 times slower if you really want to be fussy. Okay. But I hope you can see, Sydney, it's not that tough for me to speed up or slow down an electron. In fact, it's not that tough for me to design an electron gun, essentially, something that shoots out a nice steady beam of electrons by just having 2 parallel plates, have a source for electrons right here, cut a slit in the middle, and I'll get a pretty straight beam. I mean, a few might escape at like a 1-degree angle, but if I make that slit really, 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 really narrow, they're going to have to be going almost dead straight to get through it. Yes? Let's build a TV. So a CRT is a cathode ray tube. In the simplest cathode ray tube, a beam of electrons is accelerated by one set of plates, like this, and then it's deflected by another set of plates. So I'll show you what I mean. Let me zoom in. Here we have negatively charged, positively charged. So which way does that electron want to move? To the right. Now, some electrons will hit, don't write this down, there and there. What I want to get is a nice straight beam. So I drill a really, really small slit right there. And I do one more thing. I'm not going to include this in the diagram, but what I do is I put a negative plate right here and another negative plate right here, because where will that tend to push the electrons? Towards the dead center. We can really get a nice narrow beam, but I'm going to get rid of that clutters up the diagram. So we get electrons up to speed. They're traveling, they're traveling, they're traveling, they're traveling, they're traveling. Then they hit what we call our deflecting plates. The top plate is positive, the bottom plate is negative. Which way will these electrons be deflected? Up. So that when they get through, now they're traveling at maybe that angle right there. And they hit right there. By varying this voltage, can you see I can deflect it an awful lot? If I wanted to, I could hit right there. Or barely at all. If I wanted to, I could hit right there. Or by flipping the voltage, I can hit down here. Alternating current. By flipping the voltage, I could hit down there. I have complete control over wherever I want to put that electron. Okay? If I then paint this screen with a phosphorescent paint, the inside of the screen with a fluorescent paint, so that whenever an electron hits it, that causes it to give off a tiny photon right there, a dot will glow there. That's basically a television. What we do is our voltage source for the deflecting plates, we actually hook that up to the camera, because the camera is taking light in through its camera lens, and that's hitting a photoelectric plate. It's creating a voltage that exactly is identical to the amount of light that was hitting it, and that's the amount of light that's coming from the image. So without any fancy stuff, you've got a fluctuating voltage that will actually fluctuate exactly like the image that you're taking in. Very convenient. What you also do, and I didn't draw this in, is you have a second set of plates right here, but these ones are vertical so that they can deflect the electron left and right. I can deflect it up and down. I can deflect it left and right. I can put an electron anywhere on a TV screen that I want. I can make a dot appear white anywhere that I want. I can even, if I want to build a really good TV, vary the strength of the electron of the gun coming out, so I can make a dot appear white, leave it black if it doesn't get hit, or I can probably gray, just hit it with a smaller charge, smaller electron, not as fast. Oh, if I set up a system where I just continually paint the inside with a beam of electrons, and then another beam of electrons, another beam of electrons, another beam of electrons, I will paint an image, and your eyes will see that as television. Old school TVs, I think they were all at 60 hertz. That meant the inside of the screen was getting repainted every 60 times in 1 second. And that was fast enough for your eyes not to notice that you were seeing a series of images. Your eyes translated that as smooth motion. Just like when you watch a cartoon. You all know that a cartoon is actually a series of still pictures, but when you project it fast, your eyes just fill in the gaps automatically. Television, the cathode ray tube. Oh, for color TV, you have 3 electron guns, 3 electron beams, and you have 3 different types of phosphorescent paint that will react differently. And you get, I think it's red, cyan, and blue, and those colors merge into, depending on which ones you illuminate or not. Now you get color TV. So color TV was a little trickier. It took them about 15 or 20 more years to get that good. Is this perfect? Well, no, you can't get that electron beam always completely parallel. Even if you make that slit really small, some electrons that you want to come out straight will be coming out as at like a 0.1 degree angle. That's why you can tell a TV image isn't real. You can glance at it. It's not just as good as real life. And the pixels also, your eyes could spot that. So not perfect. So a cathode ray tube, a CRT, is a cathode ray tube. In the simplest cathode ray tube, a beam of electrons is accelerated by one set of plates, then deflected by another, hits a fluorescent screen which glows. So example 4, I said describe the motion of an electron beam in a CRT. We just did. In a cathode ray tube, we just did. Turn the page. We used to, and you know what, if we still had TVs of this type, I'd probably do it because I'm a nerd. We used to walk through all of the physics of the TV. We can do some of this. First of all, A says, find the speed of the electron beam after the electron gun. That's the left-hand section, those left-hand parallel plates right there. I think all of your potential turns into kinetic. You're falling all the way to the ground, metaphorically. QV equals a half m little v final squared. Hey, this is the one that we put in the box. We said the final speed is equal to the square root of 2qv over m. Do we know Q? It's an electron. Do we know the voltage? 1200 volts divided by m, the mass. We could crunch this. I'm not going to bother, but we could easily crunch this. B says, find the vertical acceleration of the beam in the deflecting plates. Well, F equals ma. The acceleration is going to be the force divided by the mass. And Jake, here's where your earlier question comes in. We would say the force is equal to Q times the electric field divided by the mass. I don't know the electric field. Aha! Between parallel plates, I do know the electric field. The electric field is equal to the voltage divided by how far apart the plates are. Plug that in there, and you can get the acceleration. In fact, if you wanted to, since you know how fast it's traveling horizontally, and you know it's traveling 5 centimeters, you could do part C. Part C says find the time. The time is just going to be the distance divided by the velocity, because horizontally no acceleration is occurring. Vertically acceleration is occurring, but horizontally no acceleration is occurring. You could find out how long it takes to travel that 5 centimeter long parallel plates. Yes? And then we could say for part D, what do they want you to find in D? Find the angle and the speed. You could say, here's Vx. Vy is going to be whatever acceleration you got from part B times time. You could get Vy, and you could find the angle. And you could then find E, the vertical displacement, and you could make a prediction as to where it's going to hit the screen. We're not going to walk through all that, but it's some neat little physics there. Turns out the television, not as complicated as you thought. The old style televisions in particular. Yeah, I heard that, but it wasn't. It was a vibrating phone. So I'll just glare and not freak out. I'm not going to give you analyze the cathode ray tube mathematically. I eventually will be asking you to explain the cathode ray tube, but I won't do it this unit because there's actually a better way to build a television. When they first did it, they used parallel plates for deflections. Then they realized, there's a much better way, and it allows us to make the televisions less long. We can use solenoids 2 units from now. Magnetic fields also can deflect it. So what's your homework? Number 1, number 2, number 3. 4 is good. Seven is good. What do we have? You know what? 8 is nice, says how long time. What, you thought number 9?
No, I guess 8 came first and 10.
Let's see. And how about 14? What's on the next page here? Find the speed of a... Nah. I won't give you. I see you guys Friday, right? So there's a good start on practicing some of these. Technically now, any question on the review is also fair game. I imagine some of you might want to start now, but some of you, since I'm doing the test after spring break, you might want to work on the review, the big ultimate package, during spring break. A couple little movies to show you here.